Yeah, well, okay. If it can go a little bit softer, it would be nice. Okay, all right. So, yeah, I will give a little bit of a general motivation from my perspective. Then also talk a little bit about multi-agent reinforcement learning. Then I will actually jump back to somehow the planning setting, because I think actually somehow thinking about how, do you do planning? How do you solve these kind of problems to begin with? That gives really the algorithmic and mathematical framework or structure to properly think about these problems. And then more towards the end, I will jump back again to, okay, what might that actually imply again for multi-agent reinforcement learning? Yeah, I will also try and point out some connections to control, as some of these results were actually developed kind of like in parallel, both in the AI communities and the decentralized control communities. So, well, if anything, that proves, I think, that these are quite fundamental, important things where multiple communities are looking at. And yeah, I think it's great to also have such many people here that are interested in those connections. All right. So yeah, well, so I kind of told this, but in slightly different way or form, I suppose. So somehow, why do we even care about multi-agent systems and uncertainty? I will talk about this so-called DEC-POMDP model, so decentralized, partially observable Markov decision processes. So for a lot of details, I can refer you to this nice book, which I, of course, also did some contributions on, but, all the nice bits are, of course, written by Christopher Amato, and everything which is incomprehensible is my bad. Yeah, and so we will then talk, like I said, a lot about, okay, what are really value functions in these kind of problems? How can we do planning? And then come back to multi-agent RL. All right. So multi-agent decision problems is what we're going to be talking about. So why do we even care about multi-agent systems to begin with? Right, and I think that there's different perspectives here. So somehow a perspective of economists, say John Nash, for instance, and these are people that are really, kind of like caring about, okay, why do intelligent agents, for instance, humans, interact in the way that they do, right? They're trying to somehow explain behavior often. On the other hand, there's also the more engineering perspective, right? And the engineer might think, well, I have a bunch of robots, and how can I get them to do something useful, right? So it's quite different goals, but yeah, all gets kind of like mangled in a little bit, right? So I'd like to think of this more as a subjective perspective. Somehow there's perhaps a particular agent or human that we're thinking about. And from that perspective, why do we care about multi-agent systems? Well, that agent will need to somehow interact with other agents or humans or things in its environment. On the other hand, we can think of more like a team or objective perspective, I like to call that. And then why do we care about multi-agent systems? Well, if we create a team of robots, there could be all kinds of benefits, right? Might be more flexible, more easy to scale up, add in more robots. If one robot fails, the other ones still continue. So we might be able to have robust, cost-effective solutions, right? And there's also the idea that, that might reduce complexity. Somehow we divide and conquer complex problems, right? Every agent can focus on different parts, perhaps. Of course, whether it really turns out to be simpler, well, perhaps not so much, but, that's one motivation. Okay, so then why, so that was why multi-agent systems, right? Some motivations. Why multi-agent learning or reinforcement learning? Well, so somehow from this subjective perspective, we can think that, well, an agent should be able to somehow learn to interact, right? There's going to be people or other agents in the environment. They don't know in advance how they will act. So somehow you need to be able to adapt and learn, right? From the engineering perspective, learning is also just a way of dealing with complexity, right? Like like in many cases where we apply machine learning. Why do we apply machine learning to face recognition? Because somehow programming this manually is very, very hard, right? So perhaps somehow we can also use learning just as a way of dealing, finding solutions to hard problems. Okay, all right. Yeah, that said, a lot of the research that I've done in this space has really motivated by well, both multi-agent systems as well as the uncertainties that are involved, right? So many settings like, well, I don't know if you have some UAVs that need to coordinate in some way, some other robotics, or if there's somehow a big incident that you're trying to perhaps have a good decision support system that will allow the emergency responders to act quickly and appropriately in good ways. You will have lots of uncertainty, right? There's uncertainty about the outcomes. There's uncertainty about what is really the state of the environment. So we have this partial observability as in POMDPs. And yeah, all of this is augmented in multi-agent settings because there can also be uncertainty about others. What are their goals, possibly, as in this morning? Now, in this lecture, we will actually focus on cooperative settings, so where all the interests are aligned, but then still they might know different things, right? They might have seen different things. So somehow, yeah, knowing what the other knows is uncertain. Okay, yeah, is there any chance of this somehow working? Well, I think there's a lot of research still to be done, but clearly we have seen quite cool types of results, right? So this is the multi-agent learning work on the capture the flag work from DeepMind from a few years already ago by now. But I was actually quite impressed by that, right? That is really somehow a multi-agent learning system that was trained, of course, you know, massive compute, et cetera, but still somehow trained to learn to play this game of capture the flag. So somehow these agents are dropped in this environment. They see these 3D images and are trained to yeah, play capture the flag like really well in that environment, right? And it's a new environment every time. So they're dropped. They somehow go out, do some reconnaissance, scouting, and they know how to take the flag and act as a team against this other team. Question, yeah. Are they what? Yeah, so from what I understood is that humans are really being beaten by these agents. Yes, that's my understanding. But yeah, so it's a really complex task, right? Yeah. So yeah, can these things somehow work? Well, in principle, I think there's good indication that we can get these kind of things possibly to work. Okay, all right. So now let me make some tempo here, because, well, you've seen all of this stuff, right? We've seen single agent decision making formalized as MDPs. We've seen single agent decision making formalized as POMDPs, where we were adding in now, you know, these sets of observations and actions. And I think we also looked already at this predator-prey example. Somehow there's a predator that's gonna catch the prey. We saw that, well, that could be partially observable, such that, well, perhaps the agent just gets this observation, well, of nothing. Or, you know, if it's within the line of sight, -1, one to the left and one up, say. And then, you know, we also know a little bit about solving these single agent problems, right? So the fully observable case, yeah, we've looked extensively at generalized policy iteration. I also mentioned that you could do other things like online planning, MCTS. So we know a bit about fully observable reinforcement learning by now, Q-learning, SARSA, these kind of things. And yeah, you can have these deep variants as well, right? In the partially observable setting, well, I didn't go super deep on this, but we've seen essentially that in those cases, yeah, the agents will need their histories, but they can also use beliefs to represent actually their state of knowledge. Somehow the belief captures everything that you need to know from the history, right? It's a belief over what is the underlying state. And that there were also then, so, you know, some solution methods that you could apply there. This kind of setting that we just saw, this kind of like, okay, well, somehow you need to learn to play Visdoom or these kind of problems. Yeah, then we really get into this partially observable reinforcement learning area where, architectures, neural network architectures with recurrent layers of various forms, transformers, of course, also nowadays a lot, are being pursued a lot currently. And that all, more or less ties back to doing policy gradient with finite state controllers, which was already, pitched and explored at the end of the 90s. Okay, good. So now what if we have multiple agents? So far, I think we're all good. Huh? No questions so far? Let me know if I'm going too fast or, last lecture. So I'm going to try to, of course, crunch as much as I can in this, right? Really see what's left. No, I will skip some stuff, but okay. So if we have multiple agents, problem becomes a bit like this now, right? Like our predator-prey problem might be, well, we have multiple predators, and they somehow need to coordinate now to catch the prey. And, we can think of this certainly if there's full observability, all the predators are able to perfectly observe the state. Yeah, really as a special case of MDP, right? Somehow, okay, the states become more complex because you need to represent now, the relative positions of all the predators. And we're going to have these joint actions. But otherwise, this pretty much still is like an MDP, right? We can think of it like an MDP with a complex state space and this complex factored action space, if you will. Right? Okay. So that's what people have been calling the multi-agent MDP model. There's somehow N agents, they take joint actions, but we can just think of it essentially as, essentially one agent with, just different action features, if you will. So yeah, this we can think of treating it as a normal MDP, where there's a puppeteer agent or something that this centralized agent would be. And it's going to select these joint actions, and then those actual agents, they just end up executing that, right? And in principle, they can also all do this in a decentralized way, right? So that puppeteer agent, you don't need to actually have to construct it, because each agent can just look up the state, think, oh, what would the centralized agent do for this particular state? What joint action? And then just execute its own component. Right? Because they can observe the state, they can also coordinate. Okay. But what now if the thing also becomes partially observable? Because, it's actually not very obvious in many real-world settings that agents will be able to perfectly observe the full state, right? Think of the emergency response type of setting. Very big challenge is to somehow know what's going on in different parts of the scenario. Okay, well, of course, somehow this now can be captured by also a framework, this decentralized partially observable Markov decision process framework, where we're going to have both joint actions, but also now joint observations, right? So all of our predators will now have this range of sight, and they're going to get their own observations. But the individual observations certainly do not reveal the state. Right? So in this kind of setting, this kind of reduction, essentially, that we did, right, to this kind of like puppeteer setting, that doesn't work anymore, right? So it could work if we have indeed somehow a centralized place. All of our agents transmit their observations to the centralized place. We actually construct this centralized physical agent. It gets in then the joint observations, and then it can send back the joint action, and then the agents would execute it. But that really requires, quite costly, quick communication capabilities, right? And the scalability of that might be quite limited. Doing something like that for, I don't know, implementing smart traffic control in a city like Amsterdam, it's not really going to scale well, right? If you need to somehow collect the sensor data of all the intersections in Amsterdam in the centralized place and then, communicate back in, I don't know, perhaps 1 second, right? Every 1 second you might need to take an action. Okay. Right. So then what can we do? Huh? All right. So as I sort of flashed or promised, like, well, perhaps multi-agent learning can be a nice way of now dealing with these complex problems. And we saw the capture the flag work, which was really promising and, well, cool looking and impressive. So perhaps we can just, throw learning at it. So I'll present 2 first ideas and also, why these might be challenging or difficult or the kind of problems that we encounter. Right? So ID 1 is individual learning. Right? So we've learned about Q-learning. So why don't we just apply Q-learning per agent? Every agent just does Q-learning. Right? And we somehow put those Q-learners together in a system and off you go. And, we'll see what happens. Right, so every agent does something like this, right? Perhaps it maintains these Q values of its individual actions based on, well, in this case, it's even a state. If it's a POM-DP, of course, that's a bit more complex even. That's kind of like this idea where, okay, I'm this agent and I'm interacting with this system, right? And I try to do Q-learning there. And so, that's not an unreasonable idea. But the problem now becomes that the environment is changing as I'm interacting with it, right? Because those other agents are also learning. So I'm now trying to apply Q-learning to this non-stationary environment, and I really don't know, how it will develop. Right? So yeah, does that even converge? Well, it turns out that if the agents can indeed all observe this centralized state, then you might have, you can show that there's going to be some convergence to a local optimum. So that's not the globally best optimal solution, right? Could still be quite bad because I always like to use this example of, well, two agents are required to somehow move a table. The other agent, hasn't learned to somehow carry its end of the table. What will I learn? I will learn it's also not worth it, right? So we end up learning that, well, both of us shouldn't make any effort and the table's not moving, right? So if I care, if the task is to move the table, that's arbitrarily bad, right? So local optimum sounds nice, but it may still be quite bad. Okay. Yeah, question. So what the question is what I mean with this. So when it converges, I think that's the question. So the system can converge if the agents observe the state. I think they do not need to observe the actions of the other agents, but yeah, I think they don't need to observe the actions of the other agents. This is a result from a paper by Klaus and Boutelier of '98. I can give you the reference and or look it up later if you're really caring about this particular detail. If the centralized state is not observable to any of the agents, yeah, there's simply no guarantees whatsoever, right? We just don't know if you apply this. All right. Well, perhaps we can do something else. ID2 is coupled learners or joint action learners, or yeah, these have a lot of different names. But it's indeed this kind of ID where we do think about it as a centralized system, right? Somehow we're going to learn about the effect of joint action. So, we might indeed do a Q-learning again. And if indeed we can observe the state, like I just said, you can actually implement it in a decentralized way. We can do this Q-learning updates now based on state and joint action. Right? So that might work, right? And indeed, if you are indeed in this kind of like a multi-agent MDP, where somehow you can observe the state and you can implement this in a way, you in principle have the same guarantees as in Q-learning. And so it will converge in the limit. But of course, in practice, the number of actions is now going to be exponential in the number of agents, and usually the number of states will also be exponential in the number of agents. That's what we just saw in this predator-prey case, right? You need to somehow retain the position of each agent. So in practice, the scalability is going to be really impaired. Right? Yeah, and of course, if it's actually decentralized, if you cannot observe the state, yeah, it's really not clear how to do this even, right? So now somehow, yeah, we can try and still do this communication ID, which, might be difficult to scale. Well, things become pretty tricky. Okay, so nice first two IDs. But if we do this individual learning, yeah, we really have no guarantees. We're dealing with this non-stationarity problem. We want to do this coupled learners, not scalable, and really we don't really know how to even do that if we don't have this instantaneous communication to a centralized place in the partially observable case. Right. Okay, yes, right, need to observe for, okay, good. So my argument here is that we really need to think about this partially observable multi-agent case separately and understand it better and have frameworks that perhaps somehow can be used to think about these things. Right? We need to somehow deal with the partial observability, and that means that we need to deal with the question of knowledge. Who knows what? Right? This is somehow the key aspect here. And that's, yeah, what we try and do in these DEC-POM DPs. So, okay, so we're gonna now, jump into, these DEC-POM DP models and, how we can define values and optimal values and do planning and these kind of things. I will need to be a little bit adaptive because I have too many slides, obviously. So I'm gonna, fast forward here and there a little bit. But hopefully I'll be able to get across the main idea. And then at the end, we return to this question of, okay, multi-agent reinforcement learning. Did we learn something now, right? Okay, all right. Well, this DEC-POM DP model is gonna be no surprise, I think, to any of you. It's really just, again, this extension of an MDP. Or a POM DP, right? So it's also partially observable. But there's now joint actions and joint observations because it's multi-agent, right? So every agent executes at every time step its individual action. As a result of the joint action, the state of the world changes according to some transition function, and a reward is issued. And in the planning case, like in the POM DP case, we assume that this reward is not observed. Right? Of course, if you're going to go to learning, you will need to somehow observe a reward signal in some way. So you can think of it then as being part of the observation, if you will. Just, a different problem. But in the planning case, somehow, we care about the expected reward. We don't actually need to observe the rewards. Okay, so state changes, reward is issued, and at that point, the environment decides on what joint observation to emit, right? Which can be correlated in a way. So, and each agent will only observe its individual component out of this joint observation. Yep. Clear? Any questions? Right. So the core thing to really understand is, okay, in this setting, Agents will only be able to observe their own actions and own observations. Right? So, okay, what's then the goal? Well, we want to find a optimal joint policy, pi star, which will specify policies for both agents or all agents, and right, but okay, this two case. Okay, what is an optimal joint policy? Well, clearly one that's gonna, maximize this value again. This is just the same as in single agent case. The difference just is the shape of those policies, right? These are individual policies that somehow need to act only on the individual knowledge. They're decentralized. Right? Okay. Yeah, then there's also this slide. So we now need to think a little bit of, okay, when do we know what, etc. Right? So when is somehow planning or possibly learning taking place? And there's different kind of things that you can think about, right? But very typically what we kind of assume is that somehow we do the planning or also often the learning, multi-agent reinforcement learning, in a offline phase first. In this phase, we now derive these policies which are decentralized. We give them to our agents, and then in the online phase, they execute this plan, only looking at their individual observations and actions taken. Right. Okay. Is there anything else that I should say about this? I don't think so. So the idea of trying to perhaps do the learning in the actual environment, of course, that's a very nice and appealing idea, right? Somehow I actually deploy my smart learning multi-agent systems on all the intersections here in Amsterdam, and over time they improve, or they adapt to the changing patterns. Clearly that would be very nice. But actually there's been surprisingly little, research really on those settings, I think. One, it's very, kind of perhaps dangerous, right? We may want to be careful about this, certainly if we have kind of algorithms where there's little guarantees of convergence, etc. And also, I think the academic community has not really then figured out what are the good assumptions, right? Because at some point, you want to collect some information about the system also still in a centralized way. So are they really going to then execute only based on their individual observations all the time? Or do we have some kind of batch learning? Or so somehow what is the right framework or the right setting to think about this is actually not so clear. But yeah, it's interesting perhaps to think about. It's perhaps one of those open questions. Okay. So what we will focus on now is, given this model, how can we compute this optimal joint policy, right? So we assume somebody has been kind enough to give us a fully specified DEC-POM-DP, including the transition model and the observation model and the reward function. And now what plans, policies do we derive an optimal joint policy, ideally, to take actions? It's a question. Yes, I'm focusing on that. Of course, you can also generalize, etc. So algorithms will change obviously a bit, but. Yeah, so you can take essentially this model, and here we have the one reward function that specifies the reward for the team based on the state and joint action. So you can have here a set of reward functions, one for each agent. And then you have what's called a partially observable stochastic gain. And that generalizes this setup. Yeah. Okay. So like poker, for instance, right? So let's get a little bit of intuition for this problem. And for that, I would like to introduce to you the tiniest possible DEC-POM-DP, right? And this two generals problem, I call it. So there's these two generals. on their own hilltops. You know, this was somehow conceived actually in times where, you know, the world was still very optimistic and looking forward, and this seemed like a very strange example. Somehow it's getting a little bit more awkward these days. This, but anyways, it is what it is. If somebody has a good idea of a very, you know, peaceful, tiniest dekpomdepie, I'm very happy to hear about it. Yeah, so there's these two generals, and they collaborate. But in between these hilltops, you know, there can be this enemy army, and that enemy army could be small or large. If it's small, you know, they somehow should attack, and then they get glory and fame because they win. But if it's large, yeah, they will not win, so that will not be great, right? This is somehow the setup, and yeah, they really can't communicate, because if somehow they communicate, you know, of course, you know, they give away other positions and the element of surprise, and that's also not good. Okay, what's happening here? Something weird. All right, so how can we formalize this? So this is now dekpomdepie, where there's two states. The enemy army is either large or small. There's two actions. Each general can observe or attack. There's also two observations. Each general can observe either a large army or a small army. Then there's some transitions. So if both the generals pick the observe action, then the state will not change, right? The either large or small army will just be there. But if at least one of them attacks, you know, magically, well, so there's some outcome, of course, and then magically the problem resets and they find themselves on these hilltops again, right? And also, they don't observe the reward, so they don't even know about this. So it's a little bit, you know, but you have to go along with it. But yeah. Okay, then there's observations. So the probability of getting a correct observation is 85%. So as an example, the probability, if the state is large, that both agents actually observe that there is a large army, is going to be 85 times 85, is a bit more than 72%. Right? Yeah, and so the reset or anything like that is not observed. Rewards are not observed. Right? Okay, what are the rewards? How do we model this task? Well, you could pick arbitrary things a little bit, I suppose, and these are a little bit arbitrary, but okay. So if one general attacks, he will always lose, also if it's a small army, right? So it's going to be -10. If both of them observe, they will have to pay a small cost of -1, because they're just sitting there. And if both attack, then it depends on the state of the problem, what payoff they get, right? If it's a large army, then yeah, it's -20, because, well, both of the generals unfortunately don't make it until they're back on the hilltop again, of course, after the problem resets. But if it's a small army, they get their fame and they get +5. Right? So this is how we can, yeah, model a dekpomdepie. So yeah, just in your mind, now suppose that we're going to act for 3 time steps, right? So 3 actions to be taken. What do you think would be a good policy? A joint policy, right? If you're one of these generals, what would you do? And what would you want the other also to do? Yes. Okay, so yeah, so the suggestion is, I think, to observe for a predetermined number of times and then attack or not attack. Well, that could be, that doesn't sound like a bad idea. That's something that we will perhaps indeed see. Okay, of course, like, well, I haven't really formalized even how exactly these policies should look like, right? What is really the domain of these policies? Or in control speak, what is the information pattern that these controllers use for their control laws, right? In normal POM-DPs, we saw that, yeah, they might use histories, but then they could use beliefs, right? In MDPs and POM-DPs, there's compact representations, namely either based on state in the MDP case or beliefs in the POM-DP case. Now, for decentralized POM-DPs, we do not know such a more compact structure, right? So if we want to have an optimal joint policy, in principle, of course there are special cases, etc., but in principle we don't know of any base, a domain of the policy, which is something else than this history that the agents should base their actions on. So we're kind of going to be stuck with histories. And of course, somehow then, you might try and do some deep learning to still, I don't know, come up with approximate representations of some way. But if we want to have really this optimal joint policy, the individual policies will really base themselves on histories. Okay, yeah. Right, so what do we get? So this is this sort of picture that I try and use often to get across. Okay, how does this DEC POM-DP work? Essentially, there's a hidden state. That hidden state will generate a joint observation. So this is somehow the environment, say, and these are the agents, the top box. Those observations are given to the agents. Each of those agents updates their own internal states with this. So essentially by remembering, typically, you need to remember the observations. They will select their actions. That's going to be executed in the state. It's going to lead to some reward and some state transitions. And then the circus starts again, right? This is how these problems then kind of like work. Okay. Well, then histories. In general, of course, all the information that an agent has is the action observation history, H. In these DEC POM-DP cases, because it's cooperative, we can actually show that just using the history of observations would be enough, right? We talked also about this in the POM-DP sort of setting. The fact that if you have deterministic policies, then you can actually figure out, look back, okay, what were the actions that you took before. So in principle, we can show that there is a deterministic optimal joint policy, and that therefore would only depend on observation histories, right? In the more general case, or if you're doing learning or trying to find out these things, you may still need these action observation histories that use H for. But this is kind of like a perfectly good representation of a policy. General observes, then if a small sees a small army, it will observe again. If it sees a small army, then it will attack. Well, something like that seems reasonable, right? Here on the left side, different policy, whereas a general who first attacks and then starts, observing later down the line might be, not so good of an idea. But still a perfectly valid policy, right? And so we can represent these policies with these kind of trees, right? The actions are in the nodes, and the observations are on the edges. Okay. All right. So I said they need to use these histories. Can't we do something like a joint belief or something? Is something you might wonder, right? And of course, somehow, if we could collect the joint actions and the joint observations in the centralized place, then we could have this puppeteer POM-DP agent that could update a form of belief, right? It would be, say, a joint belief over states. but it really requires that communication, right? So when executing in the online setting, which is really decentralized, it's just not possible to do this. That's an important thing to keep in mind. Okay, so yeah, then so this turns out to be the optimal joint policy that I asked about, right? For horizon tree, for this two generals problem, the value, expected value that they can expect to achieve is minus 2.86, well, whatever. That just turns out to be the expected value of the optimal joint policy. They can't get higher than that. And so how do they look like? Well, so how do we read this? Well, this is the policy of general 1, this of general 2. In the beginning, I observe empty history. Then if I observe a small army, I will observe. If I see a large army, I will observe. If I see a small army first and then a small army again, I will attack. Attack. But if I see a large army twice in a row, then I will observe. And in this case, the same for general 2, right? Doesn't need to be the way that way in general, but for this problem, it happens to be that the same policy is good. So anything surprising or slightly odd perhaps about this? Yes. Yeah. So that's what the impression that you get from these policies, I think. Huh? Yeah. Yeah, I think that's true. So what's of course a little bit perhaps peculiar here is that you're also attacking in these cases. Well, I first saw small and then large, or first saw large and then small. Somehow, yeah, still this attack option falls out. And specifically, yeah, particularly these two are kind of interesting to compare, right? So if I observe small first, I decide to observe. But, oh, sorry, this one should be one line down. It moved a little bit. But if I observe small first and then large, then I will attack. So that's a bit strange, right? Because intuitively, yeah, if I observe small first, the probability that the army is actually small will be higher than when I observe small first and large after that. Right? That's a bit peculiar. Yeah, I apologize. The wrong line here is highlighted. Should be this line. So why could that be? Yes. Yeah. It's perhaps tied to the reward specified when we win the battle. That's certainly the case. What aspect of that reward function do you think might lead to this behavior? Yeah, so I'm not certain if I 100% understand what you're getting to, but perhaps let me try and go back, and then we can see if what I'm saying is the same as what you mean. I think the key is here. Huh? If only one general attacks, they will lose for certain, right? So actually, it's quite important that, okay, whether it's small or large, that is important. But it's also very important that they attack at the same time. right? And so that actually ties back to the suggestion, I think, in the beginning of, okay, what could be a good solution? Well, a good solution could be perhaps to observe for some number of steps and then pick the actions, right? Because then if we decide, well, whatever happens, if we attack, we do it on the third time step, then at least we'll be coordinated about this, right? Is that what you meant as well, or? Okay, well. Then happy to still hear, but perhaps we can take it offline. I will push through a little bit and make up some time. But okay, yeah. So somehow what is really important in these kind of problems is all the things that we need to somehow balance, right? A optimal joint policy should trade off between coordination versus exploitation of the local information, right? So, you know, in MDP, we need to trade off somehow immediate reward versus possible long-term rewards. In a POMDP, we additionally need to trade off information gathering versus exploitation of that information, right? Becoming certain about what is the state such that then we can exploit it. And all of those things are also true in DEC-POMDP, but additionally we have this kind of thing where, yeah, somehow you may also really need to be coordinated. Right, so yeah, there's two kind of like extremes that you can think about. You could think about completely ignoring our own observations. I use this open loop plan that we were talking about. You know, that seems silly. We're throwing away all the local information, but it will guarantee us to be, you know, maximally coordinated. You just agree, well, on time step 3 we'll attack no matter what. We never miscoordinate. Yeah, on the other hand, other extreme, yeah, you can try of thinking of, well, I'm not going to care about this coordination at all. I'm just going to somehow try and execute something like an individual belief or something, right? I pretend that you will act random and I will just, you know, do my thing. You know, then you are using your own information, but you may not be coordinated at all. Okay, so you need to balance between those. Okay, clear? Good. Let me try and see. I am gonna have to be a bit fast here. I apologize, but I hope that you will still get across some useful bits. So a important thing is to realize this value of a joint policy, how we can compute this, right? So we now have these kind of joint policies. We saw those before. We can think of those as a tree, and then if there's 2 time steps left to go, you know, there might be a subtree that we jump to if we observed small. And then if we observe large, then we again jump to a subtree, right? So those subtrees I denoted with these Qs here. And you can kind of, you know, think of this as, yeah, almost like a part of the state, right? Like if we're going to execute this policy, well, this is the future plan that's going to happen. So in order to compute the value, yeah, we can just think of this as, you know, a form of a complex Markov reward process, as we did for policy evaluation in the single agent case. But now somehow, yeah, we need to perhaps have this history and this subtree policy which is left to be executed for both of the agents. Right? So we begin with empty histories and full subtree policies that are both this and this, which is left to be executed. And then suppose that we get the observation small, small, then we jump to this joint subtree policy. Right, that's going to be what we jump to here, and then yeah, we need to have the value of continuing from that point on. Okay, yeah, so this looks a little bit complicated, but bottom line is, yeah, it's just a form of policy evaluation on this complex Markov reward process. Yep. Okay, yeah, so like I said, really like we had before, but now what's the S in this case? Well, S now becomes this tuple of what's the history and what is the subtree policies, joint subtree policies left to execute, say, right? Yes. Yes, yes. Yes, you are completely right. These histories could be replaced by observation histories. That will be sufficient. If we have a deterministic joint policy that we're trying to evaluate, we can plug in indeed the observation histories. The reason that I did not do this here is because then, well, somehow this term becomes a bit less intuitive, because you then also need to kind of think of what was the actions that were taken so far, because somehow, okay, what is going to be the probability of joint observation is going to depend on what is the joint state. So you need to reason about what is the underlying distribution over joint states that we jump to. There's a number of different kind of formulations of these kind of value functions that you can use. This is the one that's perhaps easiest to communicate. Yes, another question. Yeah, so in this case, indeed, in this particular formulation, it's indeed the full history. Yes, yes, no, that's true. Like I said, there's a couple of different ways that you can formulate this. You can actually also have a formulation where you plug in the state. So there's a couple of different formulations that you can have. But in general, it's certainly the case that doing policy evaluation in these settings does require us to reason about all possible joint action observation histories. So that process in general is exponential. Yeah. Right. Okay, because, well, this kind of leads to what is the silliest algorithm that you could do? It's brute force search. I just, well, try and evaluate now all the possible joint policies. And yeah, clearly that's not going to be very scalable. So these are the numbers for the smallest possible DEC-POM-DP that we just saw, right, for our two generals problem. And this is the number of policies for the different possible horizons. So how many actions need to be decided upon in total. And yeah, you see that yeah, for horizon 7, we're reaching this about number of atoms in the universe level, and then for horizon 8, we are quite a bit beyond, right? So yeah, there's really a lot of policies, and then indeed actually properly evaluating also is exponential time. So each of these takes exponential time to evaluate, right? Oh, some things went wrong here again. So yeah, the complexity of optimally solving a DEC-POM-DP is nx complete, right? So guess right from doubly exponential number of possibilities, and then it takes exponential time to verify that you get at least k. So yeah, should we just give up? This feels a bit like a Don Quixote type of endeavor, right? And to some extent, I think we should. I moved to learning a bit myself, right? But that doesn't mean that we shouldn't care about these things at all, right? I think it really helps us to better understand the problem that we're facing. All of the theory of reinforcement learning is built on, or almost all of the theory of reinforcement learning is based on value functions, and how can you optimally solve MDPs? So I think we also need to understand better the multi-agent setting. And it might just be interesting. Okay, so then other things that you could do, right? So one thing is dynamic programming, which I'm not going to explain, but I'll flip through the slides nevertheless, because, well, I need to go through them. But the idea is really we try and now construct these subtree policies in a bottom-up fashion, right? So we start with well, subtree policies when there's only one time step left to go. From this we build the bigger subtrees, and from those we build the bigger subtrees. We try to kick out any things which do not seem useful. Yeah, okay, so somehow there's this idea of doing a backup where you have some subtrees of some level, tau time steps to go. Then you can plug those into this template and form a bigger subtree policy in this way. Okay, like I said, I will not really explain this. I don't have time. This scale's very fun. But then you can try and do some pruning, right? So somehow you do this thing, you do some pruning, whatever, so you have less now, and so then you don't need to generate all of these at the next time step, and then you can do some pruning again and try and approach it in this way, right? It's fascinating stuff. So then there's another approach, heuristic search, that I worked on a little bit more myself. The idea that we're going to go top down, right? So the dynamic programming perspective was kind of like plugging those things into that template to form a bigger tree. So now would be the idea to, so well, if we have this, how can we add this, right? And I will cover this a little bit. Also, I'll be quick, but to somehow get across some of the intuition of what is really now the optimal value function in a DEC-POM-DP. Right, so okay, so we can think of this as one joint policy, and the green thing is going to be a search node in our search space, right? So we're going to start with a completely unspecified joint policy. And then the idea is that, okay, well, first we specify the choices at time step 0, then at time step 1, and then at time step 2, right? This is how we're going to try and search the search space. So yeah, it looks something like this. We have the root nodes empty. Then we select choices at time step t equals 0. So that means specifying what I call a joint decision rule for time step 0. Decision rules are the choices that we make for a particular time step. And of course, you know, you could pick different ones there, right? So here, observe, observe until attack, attack, right? So then, well, we have those nodes. Then we can expand those nodes again by now selecting what we could do at the second time step, t equals 1. Of course, the number of joint decision rules for this time step, t equals 1, is going to be a lot larger, because there we're going to have to map the histories, observation histories, to actions. And again, etc., right? So here now we will need to assign actions to 8 observation histories. So there's going to be 265 children for each node at level 2. So yeah, 265 of these for each one of these, if I got it correct. So yeah, that is a very big tree, right? Well, then yeah, you can do some kind of, well, smarter search, or try to avoid generating all of these, use heuristics, all kinds of yeah, cool stuff. But what we really would want is to have perhaps, you know, an expression of these optimal value functions, and I think this perspective is useful for this, right? So one thing to realize, which is important, is that we cannot simply create the tree of joint action observation histories and then look, okay, what is the best joint action at those nodes? This will not work, right? Why not? Because the policies need to be decentralized, right? So if I have this kind of tree, where now at this node I choose AA, but at this node I end up choosing OO, attack, attack, observe, observe. Yeah, you can't do this, because in both of these cases, the first agent will have seen a small army, right? So, and it can only condition on what it observed. So you can't do that kind of like normal tree approach. But what we can do is we can view this search tree as a sort of search problem of a decision maker, right? Somehow, yeah, we will want to try and find that node that's going to lead to the best policy. So we can think of this decision maker that indeed takes these actions, namely what is the next decision rule that I'm going to add, in order to fully specify the joint policy. What I like call the decision making of the planner. Right? And so the joint decision rules are its actions. And so what are its states? Well, its states are precisely those partially specified policies, right? Partially specified joint policies. So yeah, we now have a kind of MDP, or it's not even stochastic, right? It's kind of like a search problem. But where we can somehow specify now what is the optimal value, if you want, right? So we can now construct this, well, I'll call it an MDP nevertheless, plan time MDP, where the states are essentially the decision rules taken so far. There need to be dots in between there. I apologize, right? So the delta zero until the one of the previous states. And actions those delta t, and then we can just, write down Bellman optimality equations for this, right? So we can have Q star and V star, right? Well, okay, so these are actually optimal value functions for DEC POMDPs. They may not be the most convenient, because, yeah, somehow these states are, yeah, not really easy to think about or generalize over, right? Yeah. Oh, yeah, of course. So here, so now this term is the immediate rewards, the expected reward at that stage, which, well, somehow you can compute, right? There's some, given the past joint policy, up to time step t, we can compute what is the probability over states and histories. And then, yeah, we plug that into the actual reward function, because, okay, then this is the state, and then for that history, the joint decision rule will specify a particular joint action. Okay, right? So, yeah, the dependence on that past joint policy is kind of like inconvenient, but it turns out that we can now replace this actually by a kind of statistic, right? Like a bit like beliefs in a POMDP. Right, so we can define what I call these plan time statistics. Other people have used some different terms for this, but what matters is, yeah, you have this kind of like distribution over states and joint histories. Turns out that indeed you only need it over joint observation histories. You can leave out the joint actions, but yeah, I'm just going to go with the H notation to keep it a little bit clearer now. And then we can define a value over that type of a statistic, right? So what is really relevant to determine what's the optimal value is, okay, what is the state and who knows what, right? What's the distribution over states and the distribution over who knows what, and those things are coupled. They're a joint distribution. Good. All right, so we can think of this decision-making problem of our planner and convert it to this kind of, yeah, different tree where now we have those statistics as part of those nodes, right? So does that bias anything? Well, yeah, it does, because somehow, we can now look at, well, those different decision rules actually led to the same statistics. So there's reuse there, caching. And it turns out that value function is actually also piecewise, linear, and convex over that space, right? Like we saw in POMDPs, this kind of particular structure. All right, so yes, it is actually now a special case of a POMDP, right? We can define a non-observable, actually, so it's a really special case of POMDP, a non-observable MDP for this planner, right? So the states in this non-observable POMDP are going to be what is the state and what is the history. The actions that this planner can take are still these joint decision rules. And the observation it will get is null, right? It never observes anything. But this is now a POMDP, and in this POMDP, the belief is precisely that statistic that we need, right? And yeah, so in decentralized control, indeed, people have also called this the designer's approach, for instance. You want to link some of these terms. And then, actually, yeah, so from the control community also came this insight that, yeah, you can now also extend this to deal with information which is common, right? So now, if there's somehow information that would arise that everybody could observe, you can actually include this. And that's going to take this non-observable MDP problem and turn it into an actual POMDP, right? So you can, again, have these states, which are now, well, what is the underlying state and histories of private information. we have these actions, but you might also get common information observations now. And each of those histories will lead then to different statistics that you can branch off of. Okay, yeah, this becomes a little bit involved, of course. This is called the partial history sharing information structure, I believe that was the term that they had. But somehow the idea is that we can really think of these problems from indeed the perspective of a planner and write down an appropriate model which actually corresponds to, you know, a version of POM de P that perhaps we know how to, well, at least in theory, kind of deal with, right? Okay, let me see. I might actually skip this. The idea, of course, is, yeah, all of this is still going to be based on histories. Those histories themselves will not scale. But in POM de P land, people have looked at, well, trying to take those histories and compress them in a way, right? So we can think of this as a, say, a finite state controller. Rather than having those histories, agents will have finite state controllers. There's some finite number of states that they will have, and you know, they update that internal state by choosing a next node of their controller to jump to. So you can now somehow try and also take this kind of formulation, replace the histories by those internal states, right? Now, I'm not going to be able to spend too much time here because I will still want to get back to the learning bit, but yeah. So what happens in this case is that we will define decentralized controllers where each policy corresponds in essence to its own finite state controller. So each agent has a internal state, which, you know, is a summary of the history it would have. It will take an action, get an observation, and they jump to a next node of their own controller. Yeah, the planning MDP is still a POM DP essentially that we can write down in this way, right? So okay, so this is a well, information state abstraction DEC POM DP, say, and then we can define the corresponding non-observable MDP in this way, right? We can just write down what that MDP, that special case of non-DP, special case of POM DP is, right? So yeah, states the set of augmented states, joint actions, or the actions correspond to the joint decision rules still, etc. Okay, so the planner is centralized, right? The planner's task is centralized. We all consider, you know, the centralized machine where we're doing the planning on. And then we find the policies and give them to the agents. If you want to have the planning itself decentralized, yeah, that's even, you know, a whole other can of worms that we're going to be opening up. This is really about, okay, in these kind of DEC POM DPs, what is somehow the optimal value function? And it's given because, you know, or implied by these formulations of the problem as a special case of POM DP or non-observable MDP, if you want. Yeah, if you're interested in this kind of things, Chris and I also wrote a tech report on this. I don't think a lot of people have really built upon this, but I think, you know, in terms of, well, understanding what is the optimal value, and therefore perhaps how can we learn it, etc., that might be important. Huh? You know, Gilles Dibangoye, he has actually done a little bit of work in that direction. Good. All right. Yeah, let me wrap this up. So, you know, so we've been talking about these DEC POM DPs and the planning and yada yada, and well, so it's not very scalable, but it is fun. It's kind of interesting. We did release this kind of like toolbox bunch of years ago. There's in C++ a number of these algorithms that you can give a spin if you want to try it out. So you can quite easily somehow specify some problems and try some planning out, solve this too general problem yourself if you want. Okay, let me let me jump back to multi-agent RL. Were there any questions about this planning? I know I try to put in perhaps a little bit too much, but I hope you got kind of like this main impression or understanding that, well, actually you can perhaps define, what is the optimal value function in these kind of settings by thinking of these trees. I think that's main perspective that I'm hoping that you did get. Yeah. Yeah. Yeah, yeah. Let's. I'm happy to do a little bit on the blackboard when I'm done to talk a bit more about that partial history sharing. Yeah, yeah, sure. Um, if there's a fixed step history, so you mean by building yourself, basing yourselves on a finite number of history? So I think you are suggesting that in a way you might be able to somehow prune your policies or compress them such that the tree also becomes smaller, I think. Huh? Yeah, I think that's a very interesting idea and suggestion. So how can you actually somehow compress and merge some of these things together? Well, I have one trick in order to try and scale up some of this multi-agent planning, where I indeed identify a criterion which would allow us to merge particular nodes in some cases. But yeah, in general, there might be more things to do there, I think. Yeah. Okay, then let's jump back to this learning setting, right? Why do I think that DEC-POM-DPs are possibly useful for this? Well, okay, so now we have this framework that allows us to, yeah, actually think about, who observed what at what time step. And by doing that, we can kind of formalize what this whole, well, yeah, the learning doesn't work because it's non-stationary. That's a very vague kind of like statement, of course. These individual Q learners, yeah, well, yes, non-stationarity. Okay, so great, but what does that mean? How can we address it? Because just saying, well, it's non-stationary doesn't really solve the problem. Right, so we can now somehow specify how. So I think that's nice. Right, so for instance, imagine that we have some history and we're going to do some action. Right? We can now think of how we will be affected by other agents, right? So, well, these other agents will have their history. So there's a probability distribution of what is the state and what is their history, given that I observed my history, right? And so I can then, yeah, somehow use that to well, look at, okay, what's then my expected reward? And similarly, you could do the same thing for what's going to be my expected transition, right, to the next possible state. So yeah, somehow having those components explicitly allows us to reason about what is the influence of other agents. And then, you might object somehow saying, yeah, but, my agents, they don't look like those DEC-POM-DP agents. They don't just take their actions based on their history. Well, yes, they do, right? Like a Q-learning agent is an agent that just maps some history to an action in the end, right? So the space of policies that map histories to actions actually is, is the largest space of policies that we consider. It includes all possible learning algorithms, right? All possible learning algorithms, in the end, will map to a kind of policy that maps histories to actions, or perhaps distributions over actions. Your learning algorithm might have some stochastic components or something, right? But so somehow these descriptions are really general, right? Somehow also Q-learning agents have this type of a policy. Yeah, I'm not saying that this now directly gives us the tools to completely address this, right? Because obviously the scalability issues are huge. The space of those possible policies, etc., is humongous. But it gives us somehow the tools to think about what is at least going on, right? We want to address somehow non-stationarity. Well, perhaps somehow we should kind of have some kind of idea of what policies do they correspond to, and what kind of distributions do we then get. And yeah, perhaps we can't do this closed form, but perhaps somehow we can use deep learning components to try and train those types of elements, rather than just plugging them in a simulation, saying go and hoping for the best. Okay, then let me just try and wrap up with these kind of like two kind of perspectives. A lot of the things that we've already seen, right? So there's this kind of like objective perspective of multi-agent learning, where we plan for the team, right? Remember from all the way in the beginning. So yeah, then we can think about, well, trying to do it centralized with this puppeteer, or really decentralized, which yeah, in the end, I think for scalability purposes, we would be interested in. So centralized, we can think of, well, it's fully observable perhaps, and we can apply these multi-agent MDP type of methods. So scalability issues in trying to scale up, well, in the space of joint actions are the main issues if you want to do that. If it's really partially observable, yeah, somehow you need to build on, partially observable reinforcement learning methods, RNNs and things, and these kind of things. Yeah, and joint Q-learning is really an example of this. So the scalability hurdle is really what matters here. So in the real decentralized type of approach, this DEC-PONDP reinforcement learning approach, yeah, again, we should be careful of what are we aiming for. Are we indeed trying to learn offline and then deploy? And we're in this kind of like what's now often called centralized training, decentralized execution setup, right? We have some extra things that we can actually use perhaps in this training phase. And then in the end, we output the decentralized policies. And yeah, again, we can apply all kinds of reinforcement learning techniques, value-based, such as Q-learning, policy search, or actor-critic. The actor-critic ones are, very typical for this centralized, decentralized execution, because then people often use a centralized critic, right? So this critic is only used to inform the actors. The actors are actually decentralized policies. The critic might have this centralized perspective, which people then hope that can help, and sometimes it does. But also, I would like to highlight that policy gradient itself actually is kind of, well, a method worth really knowing or understanding a bit more about, because, well, it hasn't any dependence on the Markov property. And as a result, it's actually the only method that we really know has some kind of guarantees of convergence, right, in these kind of settings. So yeah, essentially, the observation is that, and I will skip that, but it's on the next slides, that you can take the centralized value function, as you would have in the multi-agent POMDP, somehow where you have the centralized agent that can collect all the data. You write down what the policy gradient step would be for that agent. Well, actually, I can kind of show it, perhaps, even I think. You write down what the policy would be for that agent, the gradient step would be for that agent. It's this thing. And then somehow you can actually conclude that, where is it? In the multi-agent setting case. So this is the centralized gradient. In the multi-agent case, actually that gradient only depends on its own parameters, right? So yeah, I'm not going to go through all the math here. You can refer back to it and have a look. But just if you look, I do take the gradient with respect to the policy parameters. Well, the action of each agent in a decentralized setting will only depend on the parameters for its policy. And therefore just, yeah, really decentralized in an easy way. It's a very simple insight, perhaps, but also brilliant, because again, this is the only method that we really know that at least has some guarantees of converging, right? And I think rightfully that paper won a influential paper award, FAMAS, last year, I believe. Good. Yeah. The subjective perspective. Oh, yeah. Yeah. Question. Yeah. Oh, yeah. So yeah, so certainly, well, if you interpret this in actor-critic regimes, then well, what is going to be the influence of your actor, etc. And it's. I mean, I think there's a lot of work there to be done still. Chris Amato has been doing a little bit of this. Yeah, yeah, good. Yeah, just to try and wrap up and then really come full circle. Okay, so this other moral perspective, what does this boil down to? Well, so we can think indeed of this agent interacting with the world and other agents, right? And so, yeah, I like to think of this as somehow a best response model or something like that. And so you can now write down, like we saw a little bit before, right? When we were going to try and predict what is our expected reward, given, that there's some other agents and they will have their internal state, right? So yeah, we can really just, formalize that in this type of way, right? Somehow we get somehow states, an augmented state space, which include what's the underlying state and what's the internal state of the other agents. And then we can try and, just write this down. Essentially, this boils down to now a complex POM-DP. The dynamics function, which is both the transitions and observations somehow folded into one function. You can't separate them out anymore in this case, it turns out. But yeah, this just generalizes your normal POM-DP formulation. And so you have now this POM-DP, right? So as long as those other agents are somehow fixed in some way, they have some function mapping internal states to actions, but it could be a learning algorithm, right? You can formalize what POM-DP you're in. Somehow other agents are doing Q-learning. They are initialized in some way. I can somehow write, well, hypothetically, I guess, write down this model. Of course, it's going to be big, but. And so then, yeah, if you want to do RL in these kind of settings or learning in these kind of settings, yeah, it really now boils down to doing some kind of reinforcement learning in a complex setting. If somehow you could write down all the models and they are somehow very small, you might actually somehow try and apply something like POM-DP solvers, good old POM-DP solvers, algorithmic stuff. Some of that research, of course, we did in the last 20 years and some interesting things. And I think you could still do some stuff there. But clearly people like to scale up these things. So yeah, you're going to jump to the RL setting. I think a open question, probably didn't include that on the slides. But a interesting open question here is, so is now reinforcement learning for such a best response model easier or more difficult than other somehow POM-DP environments, right? On the one hand, we could say, well, perhaps it's easier for us to have some sane priors over what kind of behavior we would expect from others, right? Somehow we people are quite good at collaborating with other people, even if we don't know them in advance. So somehow for us, dealing with these POM-DP problems is doable, it seems. But yeah, on the other hand, indeed, if those other agents are learning, you are also somehow facing essentially a problem where you're never in the same world, really, right? I will talk to you again, and then you might have learned other things, new things, right? So how can I somehow extrapolate what I've learned about you by interacting with you now to the future? Possibly you would respond very different because of the things that you will learn next. Okay, yeah. well, then of course, there's all kinds of other topics. I will not dwell on this too long. I think there's a lot of interest in this multi-agent learning at the moment. Certainly, all kinds of deep learning. Learning to communicate is one of the things that's quite interesting, and people have taken some interest in. This ad hoc teamwork type of problems, like I just said, how can you somehow coordinate with agents that you didn't know before, and you don't have, like now, thousands of simulations to try and cooperate with them. We go to the football pitch and we need to play football together, right? Peter Stone's typical example. Okay, so yeah, that brings me to closing. So I think I've covered, on the one hand, a lot of kind of like different things and aspects, and we're jumping around a little bit between, well, learning and then planning and then learning again. I do hope that you were able to see a sort of common thread here, which I think really revolves around the idea that in order to make progress on these problems, we should not only just pursue, well, throwing fancy deep learning methods at them, but we should also try and be a bit more informed about what is really the algorithmic structure of these problems, right? I think, yeah, in terms of moving forward, yeah, understanding what is even, the optimal value function in a DEC-POM-DP, and that it's, yeah, fundamentally different from, somehow that normal MDP value function that we saw. Or, on the one hand, it's very similar, but it's off the planar, right? It's a different entity. You can't somehow now throw RL algorithms to your individual agents and expect them to work if the theory actually only works for the planar. Yeah, right. I think we really need these kind of like frameworks, and everybody should probably think about frameworks that enable the reasoning over what observations did the other agents get, so what do they probably know now. Even if we can't, do that exhaustively, can't scale it directly, this is somehow what is required in the problem. Because we know that the basis of the optimal value function in the end is this distribution of what is the underlying state and what is the history that everybody has. What is the state and what is the internal states, right? All of this is relevant. Who knows what? Yeah, I guess also the predictability part we talked a bit about. I think that's kind of like also good to keep in mind, right? Somehow actually doing policies where we throw away some of our private information, if we're more predictable in that way, could be worthwhile as well. Something good to keep in mind once you really get to these kind of settings. And yeah, from that perspective also, this individual Q learning, that may not be great, right? You're doing some exploration, epsilon greedy exploration at random moments. It's not predictable at all to one another. Somehow, at least we would want to have more coordinated efforts there, right? And of course, some people have looked into that. I'm not denying that at all. But yeah, I think, yeah, makes clear that it would be very important. Yeah, I think that's really it. Happy to take some questions still. Also don't want to take too much of the break. And I promise to still stick around on the Blackboard for people interested in talking about this partial information sharing idea at least. But yeah, otherwise, are there any questions left at this moment? Yes? That's a good question. Not that I am aware of. I don't think that many people have yet really try to pursue this kind of like, okay, can we now somehow understand, you know, what would be the limits of this non-stationarity, right? So I think, yeah, you could. So probably if you look at existing learning algorithms and look what they might lead to, it's very difficult to say anything. But I suppose that you could try and come up with particular learning rules such that, I don't know, the limits of what you can expect of future behavior of those as a teammate would be in some nice regime, for instance. Yeah, I think it's completely open. Oh, yeah, sorry, didn't see you there. Well, okay, so the version of the equations that I put up here, and like I said, I didn't have a lot of time to go into the details, but this is a formulation I actually quite like, which makes somehow clear that, yeah, you really don't need any Markov properties in these kind of settings, right? Somehow you can just think of, okay, well, there's some history, you take some action, and it will result in some next history. Right, so okay, so the history itself, yeah, has the Markov property, if you will. And of course, you know, if you would, you know, hope to learn to act well for a particular history, then probably you would need to revisit that history more than once, right? So yeah, either there's some resetting property or indeed some way of doing this. But in general, yeah, you don't need to have any Markov property or any states in this entire derivation. You just have somehow, well, the value function is, well, the expectation of, okay, what's going to be the history if we follow this policy? What actions will we take under this policy? And then what is the reward, right? And yeah, you can go from there and just end up with this term here that is going to be driving your gradient. Does that answer the question? Yeah, no, absolutely, sure. I'm going to be around still the rest of the afternoon, so. Yeah, so I guess so you know, in these kind of point piece, it's actually interesting. I'm also currently having this email conversation with Shimon Weitzen about this, because he also, well, he had this coma a paper, for those that of you that might know, so a counterfactual multi-agent algorithm, etc. And they had some proofs and there were some technicalities, and so we've been emailing a bit about this. But yeah, so in a sort of POMDP setting, if you're gonna do policy gradient, somehow apply to the history. Like, yeah, when can we somehow expect this to kind of work, right? Well, okay, so if the problem resets to an initial state, initial history, and, you know, histories will respond in the same way after these resets, then, you know, we can, in principle, visit all of those histories infinitely often, and all of this should kind of work. If you're really in a kind of ongoing POMDP, a world that never stops, I mean, you never revisit the same history ever, right? So yeah, what can we say? We need to then assume something about the similarities of those histories, and actually we need to assume something about our ability to understand the similarities between those histories. And that's actually, I don't know, it feels to me that there's also a little bit of an open type of, I don't know, perhaps Sean knows more about this, but yeah, but of course, you know, like what so if we now start to approximate this history with our own internal state, somehow to capture it. And then indeed, we turn the problem into something actually where we're now interacting in this sort of world where we have our own internal state that we will revisit, right? Somehow we take an action, we get back an observation, jump to the next internal state. And essentially we start to do the learning in that world. And then if that world is sufficiently close, somehow bisimilar, if you will, to the actual environment and the histories, then yeah, fine. But if they are actually quite different, yeah, you might end up, trying to learn something while the real world is actually quite different. And yeah, if it's sufficiently different, there's no guarantees, of course, that you'll do any good. All right. Any last questions? Because I feel a bit bad. I've been taking way too much time. I think everybody needs a break. So thanks for all the questions and enthusiasm. I'm happy to stick around and talk. And yeah, I think well, my impression was that it was very nice. I really enjoyed all the nice questions and participation. So yeah, looking forward to the panel and also hearing a bit more of your thoughts there. Yeah. Cheers.